So with a year and a half and a couple dozen videos between now and when I did the original Dyson Dilemma video, I thought it was about time to revisit the Fermi Paradox, and I thought it was a good idea to start by releasing more updated and improved versions of the early material. That includes this subject and its main companion video, where we take a brief but detailed look at all the proposed solutions to the Fermi Paradox. Since the original Dyson Dilemma video this is replacing tended to be the gateway video for the channel, meaning odds are this is the first time you're hearing me, let me say now what I forgot to say then. I have a speech impediment. I cannot pronounce the letter R as in a lot of these ideas that have been proposed over the years to explain this absence of aliens, this great silence among the stars. And we single out some of the better candidates for their own in-depth videos. But today we'll be looking at the notion that alien technological civilizations come into existence so infrequently that none has ever existed in our own galaxy, or likely in any of the million or so nearest galaxies. I'll be arguing to you that the strongest piece of evidence against alien civilizations existing anywhere near us is the simple fact that we can see stars in our own night sky. That the visibility of those stars, the very reason we took such an interest in the heavens and learned how truly immense the universe was, represents the strongest proof there's nobody else nearby us to share it. But the problem with most Fermi Paradox solutions is that they tend to revolve around the classic science fiction concept of flying out in fast and light ships to settle world after world. As we've explored in other videos, realistically, even if you can find a way around the speed of light, this image is probably flawed, and by and large we won't go out and terraform planets, we'll outright build them instead. And that alters the equation of the Fermi Paradox a lot, because we have to contemplate what civilizations with serious robotic automation and near unlimited energy would do. To explain that, we need to talk about hypothetical megastructures called Dyson Spheres. In the Megastructure playlist, we've looked at giant artificial structures thousands of miles long, and even outright manufacturing artificial planets, but Dyson Spheres take that a bit further. Earth gets virtually all its energy from the sun, but less than a billionth of the sun's energy falls on Earth, and even if you throw in every other planet and asteroid in our solar system, only a fraction of a millionth of the sun's energy lands on them, with the rest flying off into the void, totally wasted. If you wanted to harness that energy, you would want to surround your entire sun, and we call this a Dyson sphere. Now conceptually, you can think of it as a single giant rigid spherical shell around a star, but that wasn't what Freeman Dyson had in mind when he suggested it, nor what scientists mean when discussing it. We usually mean massive collections of orbiting bodies, ranging from giant rotating habitats like we discussed in episode 4 of the Megastructure series, or huge swarms of solar power collectors. For this reason, you will sometimes hear these called Dyson swarms instead, to emphasize that it's basically a big cloud of smaller objects, not one big rigid shell. But for our purposes today, it doesn't make a difference. Now we'll discuss some of the things you might do with all that energy, how you would go about building one, where you would come up with all the material to build one, and why you would want to build a Dyson sphere later. For the moment, what matters is that if a civilization wants to keep expanding, it can go to other stars or build up around its own, or both. The Dyson Dilemma hinges on showing they'd want to do both, could do both, and could do both on a timeline that, while very long to us, is very short in the context of the age of the universe. The timelines needed for a species to double its own numbers, if it has the inclination and resources to do so, is incredibly small compared to the timeline of the universe. It does not really matter if an organism has generations lasting only a day or 1,000 years. They can fill up space very quickly. It only takes 10 generations of doubling, just a few centuries, to increase your population 1,000-fold. So if a carbon copy of Earth existed around every yellow sun in the galaxy, and we could get people there, we could fill up all those billions of solar systems in about 1,000 years. The upside of a Dyson sphere is that a single one of them contains nearly as much living area as an entire galaxy. Our own population quadrupled during the last century, doubling basically every 50 years. But even if it took 1,000 years to double, we'd have 1 billion times as many people, enough to fill a Dyson sphere or a galaxy of Earth-like planets, in only 30,000 years. For contrast, if you took a film of the galaxy from when the universe was very young until the current day, and ran at a high speed so it played out in an hour, you could miss the whole of human history by blinking. And if you blinked again when such an expansion was going on, even a slow one, you could be looking at a lone inhabited planet when you started that second blink, and an entire filled galaxy when you were done. But if they've been building Dyson Spheres around every star as they went, you wouldn't see anything, since all the stars in the galaxy would be obscured by the Dyson Spheres. Even restrained by the speed of light, you could fill up a galaxy in just 100,000, maybe a few million years. And if travel time is your bottleneck to expansion, your population growth could move at a glacial pace and still keep up with it. That's the Dyson Dilemma in short. If an expanding civilization has the ability and desire to spread out to other stars and slowly englobe each one with a Dyson sphere until you can't see any stars at all, and even if they take tens of millions of years to do this, that is such a short period of time compared to how old the universe is that you'd expect tons of civilizations to have already done this. They could have encircled every star in the galaxy and even moved on to other galaxies, but even if no one in our galaxy had reached that point yet, or arrived from elsewhere, we'd still be able to see half-eaten galaxies billions of light years away. We could see that going on so far away that we can actually discount the more distant locations simply because the light we see from them is so old we wouldn't expect anything to have had a chance to evolve there yet. But obviously we don't. Same as with radio signals from other civilizations, we've never found a single Dyson sphere, let alone countless millions of them. We can draw two different but reasonable conclusions off this. First, they aren't there because there's no one there to build them. Either technological civilizations evolve incredibly rarely, or they kill themselves off long before being able to build such things, a concept we explored in the Fermi Paradox Apocalypse How video, where we tried to look at every plausible doomsday scenario for technological civilizations, and which we'll be looking at again soon in the Carter Doomsday Argument video. So civilizations able to build these things might be very rare or short-lived. The second option is that they either can't build them or don't wish to do so. We'll focus our attention on that idea and the problems with it for the rest of the video, but first one quick side note. I mentioned that you couldn't see these stars because they're surrounded, but that's not quite true, and it's the source of a lot of confusion about the Dyson Spheres themselves. They're not invisible, just invisible to the naked eye. Objects that absorb energy, like light from a sun, will begin to warm up, and they will also radiate energy away. The hotter they are, the faster they radiate heat. Double something's temperature, its absolute temperature, and it will pump out 6 times the radiated heat. It will also emit that at a frequency or wavelength of light dependent on the temperature. Things at room temperature, like planets with liquid water or artificial habitats constructed to house people, will radiate their heat away in a frequency of light invisible to the naked eye, but quite visible to our modern equipment, and every bit as much power will leave them as they absorb. Dyson spheres tend to be a pretty popular type of suggested dark matter. That doesn't work for a whole host of reasons, but it mostly comes from the false impression that these things are completely dark, when in reality a Dyson sphere is about the least subtle thing a civilization could ever build. The only way you could hide one would be with the sorts of entropy-defying technology that would render one a bit redundant, but more on that in a while. Summary version, they can't be seen with the naked eye, but are as easy to see as any other star. So can you build one of these? Can you get to other stars to build more of them? And would you want to? I'm going to lay out 6 conditions that, if true, make the Dyson Dilemma function. Though as we'll see in most cases where you could break these conditions, it doesn't really alter the situation much. We'll lay these conditions out, then explore their justification and possible flaws. I switched them up a bit from the original video to be a bit clearer and more comprehensive. Condition number 1. It is actually possible to build a Dyson sphere, and doing so makes sense. Obviously, if you can't build one, or you have no reason to, the whole dilemma is redundant. We'll talk about how you can build one in a bit, as well as why you would build one. Condition number 2. It is possible to engage in interstellar colonization. This is interesting because science fiction tends to imply a Dyson sphere is way high-tech and far harder to build than to go terraform planets in other solar systems, which is pretty much wrong in every respect. But it also means people tend to assume if you can do number 1, then you can do number 2 as well. But for our purposes, if you can't get to other stars, it also breaks the Dyson Dilemma because unless alien civilizations are incredibly common, we could actually miss a Dyson sphere even fairly close to us at the galactic scale. And the premise of this concept is that we would see huge emerging dark spheres, or infrared spheres, of stars disappearing as they got encompassed in a slowly expanding wave, even galaxies away. Condition number 3. No method of power generation exists which is vastly superior to stars, nor can matter and energy simply be summoned from nowhere for free. Now what I mean by this is basically perpetual motion machines and free lunches. The purpose of building a Dyson sphere is to tap into all that energy that's already being produced. If you've got something that's better, and so much better you wouldn't even care about the free energy a star emits, then you wouldn't build one. Though, as we'll see in most cases, this would result in even larger and more visible civilizations. Condition number 4. Fast and light travel, or travel to other realities or dimensions, is either not possible or not incredibly easy. Again, the premise is that we'd see solar system after solar system disappearing in a loose sphere or blob, because they want those solar systems and they grab the nearest ones first. If you could just step into some alternate reality that hosts an uninhabited carbon copy of your home world, you don't really need to expand off-world. Certain types of fast and light travel also wouldn't produce that expanding blob. More on that in a while. Our last two conditions are more psychological than scientific. Condition number 5. Civilizations do not inevitably wipe themselves out. That's an important caveat because if you kill yourself off, it's sort of hard to colonize a galaxy. This condition doesn't mean no civilization self-destruct, just that it isn't inevitable. And condition number 6. Most civilizations will expand their population, territory, and resources if they can comfortably do so. This tends to be the most controversial part of the list. I'm not quite sure why. Most folks nod their heads and say, duh. But it does seem to rub a very vocal minority the entirely wrong way, so I'll save that for last, and for the moment just point out the emphasis on comfortably do so. So let's discuss these conditions and see how they can be true and what it means if they aren't. Condition number 1 I think bugs folks because they have that image of a Dyson sphere as a giant rigid shell requiring super technologies, what I tend to call Clark tech, to build, and access to vast amounts of raw materials. None of which is true. Building Dyson swarms isn't high tech at all, and while it's a massive project, so is building homes for a few 100 million people. Building homes and factories and farms is something you do gradually with an ever-increasing pool of manpower to help, and fundamentally that is what a Dyson swarm is. Also, unlike rigid sphere versions, you can build it gradually. You start with a few components and just keep adding to it as need demands, and you stop when you're using up all your sunlight. Individual components of a Dyson swarm could be almost anything. Rotating habitats to simulate conditions on Earth, giant computer processors for some swollen artificial intelligence, swarms of power collectors. They don't have to be very sophisticated. It could literally just be endless wads of modern solar panels. Anything that takes sunlight and converts it into something we want. There's no risk of collision on these elements either. None of them generate much gravity, and while we think of these swarms as being very dense in order to get every trickle of sunlight, that ignores that space is very big and three-dimensional. In this model I've got up, we're seeing a few hundred objects all tightly packed. In reality, we'd be talking trillions of objects, all separate by huge distances. Solar panels don't need to be in the habitable zone of a solar system to function, but the habitable zone, the area where you have liquid water, is very wide, especially when things in them are artificial and can have non-spherical geometries. You'd probably build your swarm up as one ring of satellites at a time, cocked at angles. If the whole thing was compacted into a shell, it might be a few millimeters or a few meters thick, but you will be spreading that over a depth of tens of millions of miles. Even a really dense swarm would be about as dense compared to air as air is to lead. Now you might need to give these things occasional corrective shoves or blast some space debris with lasers, but you've got the entire power output of a star to work with, so it's not that hard to do. The other issue is what you do with all that power. The default use is just to light artificial habitats, but there's a lot of applications. We talked about using stars to make micro black holes to power starships recently on the channel, but another application addresses the other big issue of making a Dyson sphere, which is where you get all the mass. Now again, a Dyson sphere doesn't necessarily require much mass. If you've got millimeter-thick solar panels surrounding a sun at the distance Mercury is from the sun, then Mercury alone would have enough mass. That gets you your solar panels. As to where you get the mass for thicker stuff like rotating habitats, once you run out of raw materials from among the planets and asteroids orbiting the sun, you use the sun itself. The sun outmasses everything in the solar system by a couple orders of magnitude, by a couple more if you're only counting rocky boards with metal, not gas giants. And it gets its power from turning hydrogen into helium by fusion, something we'd like to be able to do ourselves on a more compact scale, as we discussed in the video on the impact of fusion. You can also turn helium into carbon, the stuff we make all those cool new super materials like graphene and carbon nanotubes out of. Many older stars do exactly that as they run out of hydrogen in their cores. We may well be able to turn hydrogen to helium for an energy profit ourselves in the not too distant future, and eventually be able to make energy by fusing even heavier elements into things like carbon, oxygen, nitrogen, iron, and so on. Our big problem right now isn't that we can't turn hydrogen into helium or transmute other elements. We do it in the lab all the time. Our problem is we have to spend way more energy doing it than we get out of it. It takes a lot of energy by our current methods to make heavier elements from lighter ones. Of course, if you've got all the energy of a sun to play with, and you need those heavier elements so you can have more than mostly solar panels, well, the solution is pretty obvious. No process is too inefficient if you've got a massive surplus of power you're not using for anything else. So you could convert Jupiter or Saturn into carbon bit by bit to build stuff from. But you can also pour matter straight off a sun. There's a few ways to do this, but the common concept is called star lifting, which is basically where you use a star's own power output to magnetically pull off gas from its upper atmosphere, which would constantly replenish from the compacted hot gases below. This is killing two birds with one stone, since you can convert that matter into stuff that can more practically take advantage of all that light, while decreasing the star's mass to make it live longer and glow less brightly, meaning you don't need as much material to properly Dyson it. In fact, smaller stars not only live longer, but are more efficient too, with the smallest ones converting virtually all their hydrogen into helium and energy, whereas the big ones often die before converting even a tenth of it. So if you don't have enough mass in the solar system to do much more than make thin solar collectors around your sun, you can yank matter right off the star to reduce its brightness, meaning you don't need as much mass to encompass it, while giving you more material to encompass it with more useful constructs. Ideally, your means of transmutation would produce energy for you to use as well, but if you've got to just have a big super collider running around your star, slamming atoms together to make bigger ones at a hugely inefficient rate, so be it. It's not like that power would be used for anything else. All that energy is forever lost and unusable. It's hard for me to imagine advanced civilizations, even ones that didn't want more of themselves, not grinding and gnashing their teeth at that waste. Energy that could be used for anything from making artificial habitats for nature reserves of endangered animals, to being stored for eventual use when the star dies. On any given star, there would eventually be a nice, comfortable optimum between the mass you needed to build the Dyson you want around it and the brightness it has. Sounds really high-tech, and hopefully it would be too, since our current methods of transmutation are very wasteful, but it's not something you need new physics for. Same for the construction process. There's nothing high-tech there, though more tech is better. Can you make a satellite and put it into orbit around the sun? Yes? Great. Now make 1 trillion of them. You've got a Dyson swarm. You need a real off-planet infrastructure to do this stuff, but mining and building in space is not tricky. It's getting the initial components up there to begin with that's tricky. We've looked at some of the ways of doing this in the earlier episodes of the Megastructure series. Space elevators, orbital rings, skyhooks, mass drivers, launch loops, and space fountains all hold a lot of promise, and you can click on that video link if you want to learn more. Like all the video links on this channel, they just pause this video and open the other one up in a new window. So that's condition number 1 settled. You can build a Dyson. You just do it as resources and need, permit, and require. The motivation for doing so is simply that you want to use all that otherwise wasted power. What you use it for would depend on what you want. Even if you're non-expansionist, you can always use that power to store it for super long-term usage. We previously discussed using black holes as massive batteries that will last as long compared to stars as stars do to light bulbs. But there's several mundane ways to store energy long-term, not as efficient, but even 1% efficiency is better than nothing at all. So even if you don't want that power now, that is one example of how you could use it to just prolong your civilization long after our sun and every other one has burned out. Not every hypothetical civilization we'll consider today resembles our own. The Dyson Dilemma works just fine even if the civilization is one massive single artificial superintelligence, often called a Matryoshka brain, that just runs ridiculous amounts of computing power off a whole sun. Condition number 2 was that interstellar colonization was possible. We did a whole video on that not long back, so I'll keep discussion of that short now. You can watch that for explanations of how interstellar colonization should be viable even if we never invent any cool new physics that makes it way easier. It's also very easy to get the power to send colony ships when you already have a Dyson swarm in place, or even just part of a Dyson swarm. In that video, we discussed a lot of the options, and we extended on that in the Black Hole Starship video. But the simplest one that definitely would work if you had a lot of solar collectors around your sun is to just shove your ships up to a good fraction of light speed with lasers powered by those collectors slamming off mirrors on the back of the ship, though slowing down your destination is a bit of a problem. We looked at a lot of the options for doing this in the interstellar colonization video, including how to slow down at your destination. But if you've got a decent start on building a Dyson swarm, you can get the job done. It might take a century for your colony ships to arrive, and terraforming a planet is a pretty time-consuming process, as we discussed in the video on that, but centuries and even thousands of years are nothing in the context of astronomical time. And I repeat that point a lot because it tends to be the big conceptual problem people have with the Fermi Paradox. We'll come back to this point in a bit and talk about the Hart Conjecture of the mid-70s, which the Dyson Dilemma is sort of an extension of, and the concept that mostly blunted SETI as a major endeavor. Condition 3 revolves around basically eliminating Dyson spheres as useful objects. Fundamentally, the point of a Dyson sphere is to convert stars into useful engines for whatever purpose. If you've got way better sources of power and materials than stars, you probably wouldn't bother to build one. Now, that would have to involve new physics. Physics that if it exists at all, we don't understand at all. So there's not much point of talking about it, except in two regards. We can't really speculate much about real new physical laws we don't even have a theoretical basis for, but if you've got ways to just ignore entropy, you don't need stars anymore, and you actually can hide your civilization, and you don't need to expand because you basically have infinite resources available already. But this is a problem in the Fermi Paradox because you also have no reason to hide either. No one else has a motivation to expand. And you might as well just broadcast off your trick for cheating thermodynamics so everybody else knows it and has no reason to expand and threaten you. If they've got the same trick, they don't need to expand either, whereas if they don't, they do. And they might come kicking on your door in anger just for withholding the technique, a conundrum we'll talk about more in the companion video looking at other Fermi Paradox solutions. If you gain nothing by attacking others, you need a motivation like revenge to drive you on. Like for instance, those selfish, apathetic didn't share their super technology with us when doing so would have saved countless lives and cost them nothing. This wouldn't mean they never left home. With those kinds of power resources, travel between stars wouldn't be hard, and they might just be curious. We are. That's kind of how we got all our technology to begin with. Curiosity might not be a universal trait of technological civilizations, but it's hard to imagine it's a rare one. And an ultra-energy-rich civilization with no plausible fear of other civilizations that possesses curiosity ought to be fairly chatty with its neighbors. As mentioned, we'll talk about that concept more in the companion video, where we survey the various other solutions to the Fermi Paradox. Alternatively, if you still have to obey normal physical laws, but just have some way better power source, like being able to convert matter directly into energy, then you actually worsen the Dyson Dilemma, since expansion is much easier, and you still have a motivation to do it. You wouldn't Dyson swarm your own sun, but you would still go dark since you would want to disassemble it for fuel, now or in the distant future. Plus, such a civilization would still glow very brightly in the infrared region, probably brighter than a normal Dyson swarm would. So ultimately, only entry-violating technology really gets you out of the Dyson Dilemma, and condition number 3 ends up holding even for most technologies that violate our known physical laws, either by replacing Dyson spheres with even more visible objects, or by creating a situation in which there's no reason to be silent. Condition number 4 is much the same. The new series on the channel about hypothetical faster-than-light technologies, FTL, looks at this subject in more detail, though I like to be upfront with viewers that I personally don't think real FTL is in the cards. It bugs people when I suggest we can build star-encompassing megastructures, but that the Millennium Falcon is out of our reach, but it's a Great Wall of China vs. jetpack kind of thing. One, while it certainly benefits from higher technology, is really just about manpower and effort. The other requires breakthroughs that might be a long time coming or never. There are some promising leads that let us maybe cheat the speed of light, and we talk about them in the FTL series. But for the purpose of this video, FTL is an example of where even if you got it, then it actually exacerbates the Fermi Paradox. If you can get to stars in days, not decades, interstellar colonization is pretty much a given, and you can fill up a galaxy quite quickly. This doesn't eliminate the need for Dyson Spheres though, it just delays it for a while. Once you've filled up all the planets, you still need to build Dyson Spheres if you want to expand more, and that would still probably happen as an expanding sphere, as the homeworld and oldest colonies near it fill up first and opt to build Dysons. The exception to that is any type of FTL that doesn't even care about distance. If you can just pop anywhere you want, regardless of how far away it is, then you pick the most Earth-like uninhabited planets in the whole universe, and that wouldn't result in the expanding sphere of darkness. On the other hand, if you've got super easy transport anywhere, you probably have rapid colonization and expansion, since for a long while there's no motivation to curb population growth at all, and absolutely no way to enforce it. So you wouldn't get the expanding sphere, but you would get massive population growth everywhere, and even two people, ignoring the inbreeding issues, could fill the whole universe up with their descendants in less time than it took for us to go from stone spheres to steam engines. Then they'd have to turn to Dyson Spheres. This is actually one of the major reasons I'm dubious about FTL ever being possible. I can imagine that intelligent life is pretty rare, and that the nearest ones are so far away that the light from their emerging civilizations hasn't reached us yet. But the whole universe has to come into play if you've got FTL, and maybe the whole timeline of the universe, since FTL also implies time travel. Our current physics calls it outright impossible, and it's easier for me to imagine us never having FTL workarounds that let us get to places we've never been to before, faster than light, than that the whole universe, which is way bigger than even the observer universe, if not actually outright infinite in size, never gave rise to anyone else besides us. Though we'll look at that possibility in the companion video as well. The real killer for the Dyson Dilemma from Condition 4 is if anyone ever figures out a way to pop into alternate realities, if they even exist. Because then there is a virtually infinite, and possibly literally infinite, number of copies of your own world that are the same, except nobody lives there yet. You don't bother building Dyson Spheres or terraforming planets if you've got infinite number of Earths at your fingertips. You might still have a very impressive space program, since you'd also have all those worlds to draw resources and funding from, but it will be for science and prestige efforts. You might travel to the South Pole just to prove you can do it, but you never try to make it livable if you've got lots of nicer places that are also closer at hand, so no expansion wave. You might build big transmitters and dishes to try talking to or listening for alien civilizations, but there's no galaxy encompassing outward expansion wave. And again, if you're not expanding, then the Dyson Dilemma isn't really applicable. The issue with finding aliens and not being able to hear them right now isn't an issue if they are staying homebound, unless you think that alien civilizations are so common that there are millions of them in this galaxy. We could miss a carbon copy of our own civilization, even just 1,000 light years away, and they could miss us. That detection range is constantly expanding, but it's still pretty small right now on a galactic scale. That's the concept for SETI, ultimately, and why the Hart Conjecture damaged that effort so much. And it is the Hart Conjecture that the Dyson Dilemma ultimately revolves around. Back in the early 50s, when the Fermi Paradox was first raised, we were just learning how huge and old the universe was, and we didn't have any space program at all, and we were mass-producing nukes as the Cold War got started. Nor did we have anything like the telescopes we now have, so at the time the answer seemed pretty obvious. Civilizations have their homeworld, and they are stuck on it for good or ill, and those tend to be rather pessimistic times right after 2 world wars and the invention of nukes. Enrico Fermi, for whom the paradox is named, is also known as the architect of the nuclear age and the atomic bomb, and he was also firmly opposed to the construction of the H-bomb, so he wasn't noted for his optimism about mankind's long-term survivability. Now by the mid-70s, there was a bit more optimism. Man had walked on the moon, we hadn't nuked ourselves, and we had some very tangible theoretical designs and models for not just interplanetary but interstellar spaceships. So we had to start taking very seriously the notion that interstellar colonization might be feasible. Astrophysicist Michael Hart wrote a very pivotal paper that actually spawned the Fermi Paradox as an official concept and term, and it was called the Fermi-Hart Paradox for some time. I've attached a link to that paper in the video description below that you can read, but the summary form and what it means is basically that since it appears alien civilizations could have arisen millions or even billions of years ahead of us, and since interstellar colonization seems possible, then our problem isn't that we can't hear radio signals from distant alien homeworlds. It's that we can't hear them from the leading edge of their own colonization expansion wave, or that we even hear to listen since malicious aliens might have just taken our planet back when animals living on land was becoming all the new fashion. And sure, nice aliens might leave our planet alone, but they ought to have a pretty close and easily absorbed outpost we could hear, not just their distant homeworld. A few years later, Frank Tipler added on to this with what is known as the Hart Conjecture, and basically just amounts to pointing out that automated probes with construction ability made interstellar colonization even easier, something miniaturization and 3D printing would strongly indicate is so. The notion of using robots as some kind of groundbreaking concept might seem a bit alien nowadays, but remember, this is when computers smaller than a car that could play tic-tac-toe was still considered brand new. The big weakness of SETI, and the source of a lot of criticism towards it, tends to be this concept though, that if alien civilizations are around, it's not their homeworlds we need to look for, it's their nearest colonies, which ought to be everywhere by now if even one civilization had arisen in the galaxy even just a few million years ahead of us. Of course they might all be dead, having never expanded and not have transmitted radio signals for very long, which brings us to condition number 5. Condition number 5, the notion that species don't inevitably wipe themselves out, was something we looked at in detail in the Fermi Paradox Apocalypse How video, and we saw there that actually taking a civilization out for keeps was a lot harder than we tend to think. But in the context of the Fermi Paradox, it doesn't matter if some do blow themselves up, it matters if some don't. If 1,000 civilizations arose in our galaxy in the last billion years, it would only have taken one of them not killing themselves off and going on to expand, or even just not killing themselves off but deciding expansion wasn't viable, but a great big radio transmitter was, to break the great silence. And if expansion isn't viable, then you don't need to be afraid of someone kicking your door down and taking your planet since they can't. So you might as well talk to others. The key word in condition 5 is inevitable. Because 1,000 civilizations coming into existence over a billion years in our galaxy is actually pretty pessimistic odds for development, since there's probably been tens of millions of neo-replicas of Earth-like planets life might have spawned on in our galaxy alone. Yet the Dyson Dilemma goes beyond our galaxy to encompass any close enough for us to have been able to receive light from that galaxy, which isn't so old no planet there could plausibly have developed civilizations when that light left. Even if you're on the pessimistic side about technological civilizations emerging, say just one per galaxy so far, that's a lot of galaxies in range, millions of them, and it's hard to imagine civilizations kill themselves off even 99% of the time, which would still mean at only one per galaxy and only 1% surviving, that many thousands had done so that we should be able to see. And keep in mind, it only counts for the Fermi Paradox if the obliteration results in no intelligent life with any desire to expand remaining. So a hyper-aggressive artificial intelligence that wipes out its creators doesn't count any more than our replacement of the Neanderthals does. Again, we go over this in more detail in the Apocalypse How video, but for our purposes, so long as any decently non-zero percentage of civilization survive, it doesn't work for the Fermi Paradox. This leads us to our last condition, number 6. Most civilizations will expand their population, territory, and resources if they can comfortably do so. I've never heard a good counter-argument to this, and I'm quite receptive to them since, even though the Dyson Dilemma is my own brainchild, I actually kind of despise it. I detest the notion that the universe could be so huge and old, yet basically empty, so I keep an ear out for any good challenge to the idea. But so far the closest and most common one is usually to point out that developed nations have low or even negative birth rates. That obviously is not a counter-argument, and I blame myself for not putting the word comfortably in bold last time. Find me a historic example of where a civilization, for at least 10 generations, existed well below its carrying capacity, which is the maximum population a given place can support with available technology, and had no growth that entire time, and I will revisit the issue. And remember, well below carrying capacity, which would mean they could support, with what they had for space and technology, many times what they did, and had zero growth the whole time. If you can't find one of those, then you have no valid contradiction to condition number 6. At least not a historical or modern one. And there certainly isn't an example in nature. Organisms on Earth reproduce even when it's not only not comfortable, but actively a bad idea to do so. Only the food chain and predators keep that in check, and technological civilizations wouldn't be expected to have any predators preying on them. And this being the Fermi Paradox, we still only care if everyone does it, not if some or even most do. So even if we could find a historical example of where a stable civilization had existed for many generations with no growth, when they could comfortably have increased their numbers, it changes little since it's the example of any civilization that has grown when it could do so that actually caused the dilemma, and there's obviously been tons of those. This is made even worse if a civilization develops means of seriously prolonging lifespans, a concept we'll examine when we take a look at transhumanism and immortality in the near future. When you live thousands or even millions of years, it's hard to imagine you wouldn't want to have a child at least once in all that time, if there's no pressing resource shortage to deter you. When you're building Dyson Spheres, you're also not knocking over forests. You're building habitats from previously dead rock that forests can grow in. To break condition number 6, you'd need to show that intelligent civilizations consider a dead asteroid to be more valuable than living organisms, or digital artificial intelligences, same difference. And you need to show they all would, because if even 1 in a million didn't, then they would rapidly outnumber the other million civilizations combined. Evolution favors aggressive critters who like to multiply, and the difference with intelligent creatures is that they will at least consider curbing their growth when not doing so endangers them as a culture. But the whole point of condition number 6 is that they will grow if it doesn't endanger them. Nor are all those rocks in space some sort of eternal stockpile you can tap at need. Orbits decay, flinging asteroids and planets out into the void or dumping them into stars. Stars themselves burn through mountains worth of fusion fuel every day and convert that into power that is forever wasted. It's not knocking over virgin forest for farmland. It's use or lose resources that diminish every year and serve no purpose unused. Now, there's no breaks in condition 6 that I've heard of, but there are a couple maybes that get brought up. They don't appear to work, but on initial inspection sound like they do. The first is that civilizations might go digital, convert yourself into a computer or get replaced by them. That's entirely plausible, but it doesn't really matter. You ought to be able to support a lot more people off the same power supply if they're cyborgs or outright computer programs. Growing food isn't a terribly efficient process compared to just running yourself on electricity if you can do that. But sort of like how faster light travel just delays the Dyson Dilemma while you fill up the easy-to-reach and terraform planets, you will still get a maximum population of computer people. No matter how much more efficient you make your processing and data storage, you will max out eventually, and then if you want to expand more, you'll need to move outwards to empty spaces or import material from elsewhere. We'll look at the concept of such societies more in the aforementioned transhumanism video, and also in the one on simulation hypothesis, the notion that we might all live inside a giant computer program. But it doesn't change that if you want more people, you eventually need external resources. And why would you not want more people? More artists, more scientists, more actors and musicians and novelists and great thinkers. But a better way of looking at it would be, would you be willing to kill to stop it? Because even if you and most of your civilization likes your total population just as it is, unless that opinion is universally held by every member of your civilization, and every other civilization, you'd have to be willing to actually chase down and blow up any rebellious members of your civilization guilty of wanting to set up shop elsewhere. Or somebody's going to do it, and odds are their descendants will share their expansionist preferences. Of course, it could be a single mind, the giant plant-sized or sun-sized computer we mentioned, and it might have no desire to reproduce. It doesn't want to send a seed to another solar system to become a rival. That still doesn't really matter though, because it just announced a motivation. It doesn't want a rival, meaning it probably wants to live, which could probably be taken for granted since while biological organisms have survival built in, and would probably transmit that as part of their cultural mindset and ideology even to non-biological descendants, it's kind of hard to imagine survival-oriented civilizations being wiped out by an entity or entities that weren't survival-oriented. And in that motivation, especially for some giant supermind, we get the same expansion wave. Its life is really measured not in classic time, but in total processes done, flops or floating point operations. But either way, the more calculation power it has, the longer it can run them, the better. And I already mentioned how things like black holes can be used to store power for insane periods of time, even compared to solar lifetimes. You don't need full-blown human-level intelligence on your robot probe sent out to strip mine other solar systems to bring those resources back to your hoard, and you can even make a Dyson swarm out of stars. Not only can you use a star's own power to pull mass out of it, you can use a star's own power to move it. All Dyson spheres are starships, very slow ones, but you can reflect your sunlight or waste heat, or both, asymmetrically rather than omnidirectionally to provide thrust. There are all sorts of ways you can harvest your galaxy and crunch it into a smaller volume for long-term storage, just from available known science. So if you're a big omni-brain who just wants to live as long as you can, hoping to figure out an ultimate cheat code for entropy and the heat death of the universe, sending non-sentient robots to harvest everything in sight for your horde will do the trick. And the same for any other civilization too. A culture might decide it only wants X number of people, and really will kill off anyone who tries to flee to found a new colony. Maybe they feel physical or ideological mutation will ultimately spawn an enemy, but that doesn't stop them from wanting to persist as long as possible and harvesting the galaxy remotely. And such a reverse blockade, keeping anyone from leaving, is much easier to enforce if you've got millions of semi-intelligent robotic harvesting fleets roaming the galaxy who can notice, attack, monitor, or report anyone who managed to sneak away. So that's the Dyson Dilemma. Fundamentally, the concept that while life might be incredibly common in the universe, technological civilizations are probably so rare and spread out that there is not even one within a billion light years of us. The biggest point of evidence for it being that we can see the stars with our own eyes. Why this should be, that technological civilizations are so rare, the Dyson Dilemma doesn't answer, and we will look at that more properly in the companion video. Over in the Comprehensive Solutions companion video, we'll take a look at a lot of the other post-Fermi Paradox solutions and look at their strengths and weaknesses. But that's it for this topic today. Comments and questions are welcome. I try to reply to as many as possible. If you enjoyed this video, hit the like button and share it with others. And if you want alerts when new videos come out, hit the subscribe button. In the meantime, try out some of these other video playlists. As always, thanks for watching and have a great day.